Yeah, good afternoon, everyone. I'll give you a little idea about what we've been up to this last fiscal year in this project. Let's see. Here's the abstract. If you're so inclined, you can take a look at that whenever. Project members are mostly from the near surface geophysics section in the Central Canada Division, and then we've got Benoit, who's in the Northern Canada Division, all here in Ottawa. Our collaborators are the Rideau Valley Conservation Authority, the Ottawa Riverkeeper, and the City of Ottawa, who grants us access to the land for some of the for all of the field work in the project. So the motivation for this project is that stream water aquifer exchange is not well understood for urban hydrological systems. Historically, these systems are treated as sort of in and out systems where something goes into the urban catchment and it comes out at the end sometime later. But we know that that's not the case. Particularly in the context of contaminant transport. So this map is from the Ontario Provincial Groundwater Monitoring Network. And you can see elevated samples of chloride in groundwater all over the region. So, we know that contaminants may reside in the system or may be transported from the urban stream into groundwater or from groundwater back into the stream. So we have a more complicated system, and retention of these contaminants can result in persistent or long-term threats to water quality, both for drinking water or aquatic life. So the objective of this project is to look at electrical geophysical methods as a tool for better understanding water exchange in these urban stream settings. In particular, we want to use geophysics to capture some of the subsurface spatial complexity and the system evolution for these streams as we load the stream with what we have as an anthropogenic tracer here, which is chloride. And at the same time, we can sort of assess the occurrence of that contaminant storage and release in this urban stream setting. So we had some issues in the first year of this program. So this past year has really been the first year that we've been on the ground running. And our first year was primarily concerned with site selection. This is a map of the Ottawa area. You can see the Ottawa River, and then superficial geology is overlain on top of that. And then everything red is what's designated as a highly vulnerable aquifer. In this case, it's usually because we have a thick sequence of coarse glacial or glacial fluvial deposits, or because we have very thin drift entirely, so that we're close to the bedrock aquifer. And then that dark black line you can see there is the intake protection zone for the Britannia drinking water intake in the Ottawa River. So basically anything within that black line is essentially 2 hours away from the drinking water intake. So we used these sort of high impact areas and we used that. So we started to look at the catchments that passed through these high impact areas and, walk up and down those catchments. And we combined that with groundwater indicators that are mapped intermittently by the Rideau Valley Conservation Authority. And based on all that information, we came up with a few target catchments and then a few target sites along those catchments, where we then went in for a sampling, preliminary sampling campaigns. So that's water samples and geophysical data collection. And some of the first water samples, or some of the water samples we collected were for radon as a groundwater indicator. So on the left here, you can see radon just in 3 example catchments. And you can see that this is from August 2025. You can see the level of radon in those catchments varies considerably. And so we would interpret this higher radon level as having a higher contribution from groundwater. And so we can sort of zero in on those sites that, maybe have more groundwater influence. If we look at this same site in downstream. So this was in August. This is in October on the right-hand side in at this one site in Graham Creek. And if we look at radon samples taken downstream, we see an interesting pattern there where we have low radon upstream, and then we have this spike in radon, and then sort of this exponential decrease in radon as we go downstream. So again, we can interpret those high radon levels as indicative of groundwater contribution, and we can maybe use that information to try to locate areas where we have significant groundwater surface water exchange. Of course, there's lots of other factors in in picking sites, not the least of which is logistics. But we did zero in on Graham Creek as our most likely candidate. And so some of the others preliminary data would be the electrical geophysics. So this is a cross section across Graham Creek showing high electrical resistivity in red and low electrical resistivity in blue, or high conductivity in blue and low conductivity in red. And you can see the stream shows up as relatively high conductivity. We have the saturated zone, and then we have these unsaturated banks. And we use these background electrical geophysical data help us get an idea on, sort of the initial conditions, the geology. We also have sections, down the stream and at different locations along the stream to help us put that together. But from an experimental standpoint, it's important to see that the resistivity of the system is quite separable. We have good distinction between the unsaturated sediments, the saturated zone, and the stream itself. So that if we were to introduce a conductive tracer into this system, we have high confidence in being able to see that tracer and quantify the movement of that tracer. And these data here are from the Ottawa Riverkeeper in Graham Creek, not at this exact site, but downstream a little bit. And this black arrow shows the time when these geophysical data were collected. So you can see we're in a relatively low conductivity period in the summer, but then we expect that conductivity to spike up quite a lot in the winter, and that's when we'll have that basically that anthropogenic tracer input that we'll be able to track. And based on the electrical conductivity that we see in the summer, we should have a really good chance of tracking the evolution of that. Just some other preliminary samples. This is the electrical conductivity as a function of the chloride concentration. And as expected, there's pretty good predictive power there based on how much chloride is in the water. This relationship can change as we load the stream with more suspended sediment or other dissolved solids. So it needs to be reassessed and monitored, but it's just evidence of the ability to use the conductivity of the subsurface as a chloride proxy. And then on the right here, we have chloride-bromide ratios, along with some of the standard values for different types of waters. So we have precipitation, groundwater, seawater. And you can see that the values for Graham Creek lie pretty solidly in the halite zone. So the source of chloride is most likely road salt application in this case. But even in these summer months, we're up in, we're above 120 milligrams per liter, which is kind of the limit for chronic toxicity as determined by the Council for, I can't remember, CMME, Canadian Ministers of the Environment. Yeah. So it's work in progress. We hope this summer that we'll get installation of the site done and start being able to acquire 3D geophysical data. At the same time, we'll be deploying our in-stream sensors all over the catchment. This is something we've been working on, these do-it-yourself in-stream sensors. These are, so everything's off the shelf, microelectronics, Raspberry Pi. And for less than $100, someone can put one of these sensors together compared to several $1,000s for sort of research grade materials. And the idea here is that, this kind of sensor could be picked up by sort of nonprofit or ecological organizations for sort of distribution across an urban environment at a relatively with a relatively small budget. So hopefully we'll begin testing these this summer, and then working on just handling all the data as it comes in. So that's my email. If you'd like to contact me, you're welcome to get in touch, or if you have any questions, I'm happy to answer those.